I'm Qingyu from the University of Tokyo and alongside X. I'm glad to introduce our work, Divergence Optimization for Noisy Universal Domain Adaptation. As the task of General Unsupervised Domain Adaptation, also called UDA, we have a dataset from source domain and a dataset from target domain. The source samples are labeled and the target samples are unlabeled. The goal of UDA is train a model with this data and try to get better prediction accuracy of the target samples. In the general UDA, the source domain and the target domain share the same classes. When there are some classes only appear in the source domain and not contained in the target domain, we call this setting partial UDA, where the number of source classes is larger than that of target classes, and we call these additional classes in the source domain source private classes. As another scenario is that there are some additional classes exist in the target domain, named target private classes. Since the target samples do not have any labels, this setting forms an open set problem, and is named open set UDA. In open set UDA, we need to detect these target private classes in the target domain as an unified unknown class. When the source private classes and target private classes exist at the same time, it is named universal UDA, which is a popular UDA setting recently. In our work based on universal UDA, we proposed a new problem setting, noisy universal UDA, where we introduce some noisy labels into the labeled source sample. As we can see in this figure, some labels of source samples can be run in this setting. For example, a bag image can be labeled as bike, and a speaker image can be labeled as mouse. We think this setting is more realistic because the dataset collected from internet may contain this kind of noisy samples. As related works, many works focused on noisy label problem, partial UDA and open-set UDA separately. The ENN is a general UDA method, and TCL works on noisy labels in UDA. ETN and STA solves partial UDA and open-set UDA respectively. UAN is a universal UDA method, and DANCE is the state-of-the-art UDA method. The goal of our method is to solve all these problems at the same time. The overall concept of our method is when we have two different networks having different parameters with the same noisy dataset, the two networks will provide distinct views of each sample. This helps us to detect noisy samples by calculating the divergence between the outputs of the two classifiers. For the clean samples whose image and label are paired correctly, the two networks will output the same result with high confidence. We calculate the entropy of each output, the cross-entropy between the two classifiers, and add them as the divergence. For clean samples, the divergence is low. On the other hand, for the noisy samples whose image and label are not paired, the two networks tend to output the different result and their confidence is low, so the divergence for these samples tends to be higher. In the setting of noisy universal UDA, the noisy source samples are absolute noisy samples. For target private samples, since they do not belong to any source classes, assigning any label to them are not correct. They can also be considered as noisy data. So our multi-view learning concept can deal with these two kinds of samples at the same time. The networks used in our method contains one common feature generator and two separated classifiers. First, labeled source samples are input into the network and the two outputs of probabilities are obtained. We calculate the supervised loss with the ground truth labels and the divergence between the two outputs. The sum of them are used as the loss of each sample. We choose the samples having small loss as the clean source samples to update the whole network to avoid the effect of noisy samples. This is a figure that shows the first step. The blue samples are source samples and gray samples are target samples. We built two classifiers by ignoring noisy source samples having large loss. Then we trained the network with unlabeled target samples. For the outputs of target samples, we calculate the divergence between the two classifiers of each sample, and separate the divergence of these samples. The samples having large divergence are considered as target private samples, and we further increase the divergence of these samples. On the other hand, we further decrease the divergence of the samples having small divergence, and these samples are considered to be common samples. What we want to do in this step is to align the distribution of target samples according to the divergence. For target common samples, we try to move them into a small divergence area, and for target private samples, they are moved into large divergence area. We are close to the gap of the two classifiers. As the next step, we try to only update the two classifiers by maximizing the divergence when the feature generator is fixed. This operation is helpful to detect target samples far from the cluster of source samples. In this step, we also use source samples to keep the classifiers to classify source samples correctly. Finally, we update the generator when the classifiers are fixed. We select the samples having divergence as target common samples and try to minimize the divergence of these samples. By minimizing the divergence, it is able to align these target common samples into the cluster of source samples while keeping target private samples far from common samples. During the inference, we feed the test target samples into the network and calculate the divergence between the classifiers. If the divergence is larger than the threshold, this sample is considered as target private samples. If its divergence is smaller than the threshold, it will be considered as common samples, and we further using probabilities to predict the class label. This animation shows the result on toy data. Red, blue, and orange points indicate the three classes of the source samples, where the orange classes is the source private class. Some source samples have noisy labels. White points represent target samples, and the target samples at the right bottom are target private samples. The dashed and normal lines are two different boundaries in our method for identifying the red class. The pink, light blue, and light yellow regions shows the result of both classifiers are red, blue, and orange, respectively. The gray regions are detected as the target private classes having large divergence. By training with our proposed method, the classifiers are not affected by the noise source samples, and target private samples exist in the area having large divergence. For the experiments on benchmarks, we used 3 datasets and added 2 types of noise, fair flip and symmetry, with 20% or 45% noise level to the data. The figure on the right shows the noise transition metric of fair flip, where the label of one class may be replaced by its neighbor class. And this figure shows the noise transition metric of symmetric label noise, where the label of one class may be replaced by any other classes. This table shows the comparison of test accuracy between our method and existing method. We can see in the 3 datasets and 4 kinds of noise types, our method achieved best performance in most tasks. We also show the probability density function of the divergence of common and target private samples in this figure. We can find the divergence of common and target private samples is separated, which means we can detect target private samples according to the divergence. This is the conclusion of our work. Thank you for listening.